Okay. Well, thank you for the invitation to be here. It's a pleasure to be in Miami for the first time and to be speaking at this conference. So I will talk today about interesting connections that I found between symplectic embeddings, billiards, and finally the Toda lattice. So let's begin with, I think everybody's familiar, but to be on the same page, I'm really only going to talk about subsets of R2N. So we fix our symplectic form in R2N to be the sum of dqi dpi. And the first, question, which is a typical classification question, is given two subsets of R2N, when is there a diffeomorphism that preserves the symplectic form? So we call that a symplectomorphism. Usually this question is very hard. Here's a very simple example of a symplectomorphism. You just stick a disk into an ellipse in R2. And there are many easy things one can do in dimension 2 that preserve the area form. But in higher dimensions, this turns out to be pretty hard in general. So one thing that we can do if the question is too hard is we can weaken it. So when does there exist an embedding from one manifold into the other that preserves the symplectic form? Actually, today I will talk about some symplectomorphisms on the nose, but they are actually inspired by a line of research coming from symplectic embeddings. So let me tell you some things that maybe most of you have already seen, so that we can talk about symplectic capacities. So if you take our symplectic form and we take the wedge product of it with itself n times, we get a volume form in R2N, which implies that if you map an embedding, a diffeomorphism, any kind of map that preserves the symplectic form, then you preserve the volume form as well. Okay, so for example, if we take the ball in the cylinder, so this is like the seminal question in symplectic topology, is if you take the ball and then we take the cylinder, which is the Z2n, where you fix Q1 and P1 to be in a disk, and then you let all the other variables loose, then you could ask, when does the ball embed into the cylinder? So that's kind of an interesting question. And I guess the reason this is interesting is that you can find, it's not so hard to find a volume preserving map embedding from the ball into the cylinder. But what's really, really interesting is that Gromov proved in 1985 that you cannot do that symplectically, unless the ball already fits in the cylinder by inclusion. Okay, so I think probably most of you, if not all of you, are aware of this result, not only because it's very interesting, but also because it introduced techniques of pseudo-holomorphic curves into symplectic geometry, and it's been a big revolution ever since with Floer homology and many other things. Okay, so you can think about it in terms of symplectic shadows. So the symplectic shadow has to be at least the same size as the previous. And just to point out how this is quite subtle, if you change the cylinder and now instead of saying that P1 and Q1 are in a disk, if you set Q1 and Q2 in a disk, then there are no obstructions. You can do anything you want. So you can embed this for any epsilon. In fact, all these tildes are symplectomorphic because you can just scale up the Q1, Q2 and then scale down the P1, P2 as much as you want. So remember, and this is because the symplectic form really pairs Qi with Pi. Okay. So now an interesting way to encode the idea of symplectic embeddings is using the notion of symplectic capacities. So a symplectic capacity is a function that assigns to a subset of R2N a number that could be 0 or infinite. Usually it's a number between 0 and infinity. And it has basically three properties that are fundamental. One is that it scales with as R squared, so it's quadratic, which gives a sense of being a symplectic invariant. The second one is that if there exists a symplectic embedding, then there is an inequality in the capacity, so it provides an obstruction for the existence of symplectic embeddings. And finally, it's non-trivial, meaning that the ball has positive capacity and the cylinder has non-infinite capacity. So this condition in particular says it can't be related to the volume. So it can't be just the volume to some power. So that's, and it can't be identically zero. Okay. And then we say the capacity is normalized if the capacity of the ball and the capacity of the cylinder are the same. And we usually take that to be pi r squared. Okay. And notice that just the existence of a normalized symplectic capacity is equivalent to Gromov's non-squeezing theorem. So this is a quick observation, but it's kind of interesting also from the historical point of view. Just constructing, if you're able to construct a normalized symplectic capacity, then you have a different proof of Gromov's non-squeezing theorem. Okay, so in the next slide, I will show you, I'll name a few capacities. And I just want to point out that, people like Eklund and Hofer or Hofer-Zender, they constructed symplectic capacities without using pseudo-holomorphic curves a few years after Gromov. And that's another proof of, that implies another proof of Gromov's non-squeezing theorem. And of course, later on, people constructed a lot of other capacities I'll point out in the next slide. Okay, any questions or comments? Okay, so the simplest capacities are the Gromov width. So that's the biggest ball, that's pi r squared of the largest ball that you can embed into X. And the cylindrical capacity, which is basically the smallest cylinder into which you can embed your manifold. Okay, and it's not hard to see that any normalized capacity has to be in between the Gromov width and the cylindrical capacity. Okay, so here are some other examples of normalized capacities. And I think many of you have seen this before, but I just want to show you the variety of things that exist in the literature. So the first one, and I think this is where the name capacity was first given, was in the work of Eklund and Hofer in the late 80s. So the first Eklund-Hofer capacity, in fact, they constructed a sequence of capacities which are not normalized, but the first one is. And this involves methods from functional analysis, setting in the setting of H1 half, the Hilbert space with H1 half. And then a little bit later, Hofer and Zender constructed this capacity that's usually called Hofer and Zender capacity. And that's a little bit easier to construct and also easier to compute. And then around the same time, there's this work by Flohr and Hofer that constructs the capacity. And this time it uses holomorphic curves. So by using symplectic homology. And then much more recently, a work of Jean Gut and Michael Hutchings constructs a capacity from contact homology, which really means, S1, positive S1 covariance symplectic homology. But anyway, something related to contact homology. And if anybody wants more details, I can say something else about it. And it turns out that this capacity here actually coincides with the first Eklund-Hofer capacity. And also both are sequences of capacities that coincide for at least star-shaped domains. And finally, I just want to mention that there's a capacity in dimension 4 that's very powerful, coming from embedded contact homology. Okay, so here are a list of normalized capacities. You might ask, why do you care? And the reason we care is because using them, some of them are easier to define, some of them are easier to compute, and almost all of them give interesting obstructions to symplectic embeddings, some of which are sharp. Okay, so I'm not going to go into the history of symplectic embeddings. I mean, you can see many talks about that. But I want to talk about a specific conjecture about capacities, which is due to Viterbo. So first of all, notice that this is a simple calculation. If you have a compact set, then the Gromov width satisfies a very simple inequality. And this is just because a symplectic embedding is a volume preserving embedding. So you can just compute the volume of the ball, and then it's because the volume of the ball is basically pi r squared to the power n over n factorial. So that will give you this inequality. And it's also relatively easy to show that if you take any random compact set and you try to do the same inequality, it won't hold for very crazy sets. And in fact, what Viterbo conjectured is that this inequality holds for every normalized symplectic capacity for convex sets. And he had enough reason to believe in that based on examples. Okay, and this conjecture is still open. I think that it is definitely believed to be true in dimension 4. In higher dimensions, I think nobody really claims that the conjecture is false, but maybe there's a little less evidence that the conjecture is true. But anyway, this is the conjecture. And then also, it's easy to see that this is an equality when you have a ball. But the conjecture also says, that we have equality if and only if X is symplectomorphic to a ball. Okay, any questions? Okay, so now I'm going to take a little detour and tell you guys about a different conjecture. Actually, sorry, before that, let me just weaken the conjecture a little bit. So if we take a compact and convex set, now we can look, let's just suppose first that it has smooth boundary. And then we can look at the minimum period of a Rabe orbit on the boundary. Okay, so this is in R2n. So we have a standard Liouville form, which is the standard primitive in R2n. It doesn't actually matter which one we take. And we look at a Rabe orbit with closed characteristic on the boundary, which we know always exists by the Weinstein conjecture in this setting. And we can look at the smallest one. So it's the theorem of a lot of people that a lot of these capacities coincide with the minimum action in this setting. Okay, so we can write down the Viterbo conjecture. So notice that the Gromov width, or neither the Gromov width nor the cylindrical capacity is one of these. But we have this capacity, which is in the middle, which is the minimum action, which coincides with a lot of these capacities for convex sets. And we can just ask the Viterbo conjecture for this capacity. So now this is kind of a systolic inequality. Okay, so we're saying that if X is a compact and convex set with smooth boundary, then the minimum action of a characteristic or a Rabe orbit on its boundary satisfies some inequality. So there is an upper bound for it that's related to the volume. Okay, so that's what I'm calling the weak Viterbo conjecture. And then of course, maybe it is true that all normalized capacities coincide on convex sets. So that is what we call this, that's what I'm going to call the strong Viterbo conjecture. And this is kind of independent of Viterbo. People were already asking these questions back in the early 90s, or maybe mid 90s. This is not exactly due to Viterbo, but it's a stronger conjecture than Viterbo. Because if we know they all coincide, and we know the Viterbo conjecture is true for the Gromov width, which is the smallest one, then the Viterbo conjecture is going to be true always. Okay. Let me just take a break. Does anybody have a question? It's not obvious. Like, I think that's part of the theorem. Like, if you just take the minimum action, it's not obvious that it's monotone. Right? You know, if you have an embedding that it would be preserved. It's true for domains with convex boundaries because of this theorem. I mean, you can say just because of the Eklund-Hofert. So on the first, the Hofert-Zander capacity. Oh, if you have a Liouville boundary. That definitely follows from the fact that it coincides with the contact homology. But in general, I don't think it's easy to say. It's basically a consequence of this theorem is that the minimum action is a capacity. Okay, so let's go on a detour. Let's talk about a completely different kind of, not completely different, still within geometry. But not symplectic geometry. So this is a famous open problem called the Mahler conjecture. So it goes like this. So we take a symmetric and compact set in Rn. And then for a set like that, we can define this polar body. So the polar body is the set of points such that when you take the inner product with every point in K, you get something that's less than or equal to 1. Okay? Another way to think of it is you can think of K as the unit ball of some norm. The norm is determined by K. And then K polar is the unit ball in the dual norm. Okay. Symmetric just means symmetric with respect to the origin. So X is in K if and only if minus X is in K. So you need that to have an actual norm. Otherwise you have, a semi-norm or something. You can still talk about polar bodies in that setting, but the Mahler conjecture will be a little different. that setting. So I want to, and it's not actually related to symplectic geometry. So that's why I have the condition symmetric. Okay. So for example, if you take the unit ball in the norm LP of radius 1, its polar is the unit ball in the norm LQ, where 1 over P plus 1 over Q equals 1. And another thing that's interesting is if you take a polytope, like a symmetric polytope, then K dual, K polar, is going to be a scaling of the dual polytope in the combinatorial sense. Okay? And of course, determining which scaling, that's going to depend on how big the polytope is. And another interesting observation is that if you take your polytope or if you take, if you take any symmetric compact and convex set and you multiply it by a matrix, by an invertible matrix, then the polar body changes appropriately. So it's easy to see that it will change by the inverse transpose applied to it. In particular, the volume of the polytope or of the set K and its polar body is preserved. The product of the two volumes is preserved. I mean, in particular, if you scale one by a constant, the other one's going to be the inverse of that constant. But it also works for linear transformations. Okay. So one thing you can see is that this product that I'm calling M of K. So M of K is the product of the volume and of the convex body and its polar. So this product is actually maximized when K is a ball or an ellipsoid. Okay, so this was proved first by Blaschke in dimensions 2 and 3, and by Santalal in higher dimensions. And this is basically something related to the isoperimetric inequality. Like you can prove it directly by doing some symmetrization process, like slice by slice, and then taking some limit. It's not extremely hard. It's kind of beautiful. So that means this product is bounded above by the volume of the ball squared. And then in 1938, Mahler was looking at this and trying to find how to get a lower bound for this product. And he proved that in dimension 2, M of K attains its minimum exactly when K is a parallelogram. So a linear transformation times a square. Okay, so this is the configuration that gives you the minimum in this product. And he conjectured a little bit later that, the next year, I guess, that in every dimension, this M of K attains its minimum when K is a hypercube. Okay. So, so let me tell you so here's the conjecture. The conjecture is that M of K, this product, is always greater than or equal to 4 to the n over n factorial. It's very easy to compute this number for a hypercube. Okay, so here's what's known about this. So in 87, Bourgain and Millman proved that this is the right order. So basically there exists some constant such that this product is greater than or equal to c to the n over n factorial. So it's bounded below and in the appropriate growth rate. And then Greg Kuperberg in 2008 showed that it's bounded by pi to the n over n factorial. So, there is a gap between pi and 4. And of course, he didn't find a sharp case, otherwise the conjecture would be disproven. But you're kind of stuck with that. And then very recently, 2020, Iri and Shibata proved that the conjecture holds in dimension 3. Okay, so then after that, it's pretty much wide open. These are the main results. So we don't know anything else in higher dimensions. But why am I talking about this right after Viterbo? You can probably guess that they are related. So let me tell you about this beautiful story. And before, let me tell you another case of equality for the Mahler conjecture. So a Harner polytope is basically a generalization of a cube. So instead of just taking products of intervals, you take products of intervals and you take the polar operation. So you can take a few products, and then you can take polars, and then you take the set of polytopes generated by products and polars, starting from the interval. So here's an example. So this is you take the octahedron and you take the product of the octahedron with the interval, and you project it to R3, or I guess R2. Okay, so it's not hard to see. This is a slightly trickier thing than for the hypercube, but you can see that for a Harner polytope, the Mahler product is the same thing. So now we can conjecture that this Mahler product is minimized precisely by the Harner polytopes, and this is open. So we don't know. We don't know anything else that minimizes the Mahler product, but we know the Harner polytopes do. Okay, so we can state the Mahler conjecture like this. So if K is a centrally symmetric compact and convex set, then the Mahler product has this lower bound that's 4 to the n over n factorial, and the equality is attained if and only if k is a Hahn polyton. So the reason I'm bringing this up is because in 2014, Artsen, Avedon, Karstaff, and Ostrover proved that the weak Viterbo conjecture, the systolic inequality type 1, implies the Mahler conjecture. Okay, so here we have a string of implications. So we have the strong Viterbo, which could still be true. So that implies the regular Viterbo conjecture, which implies the weak Viterbo, which implies Mahler. And this is going to be relevant for what I'm going to tell you later in the talk, which is why I'm mentioning it. Okay, so let me explain the proof of this, and so you can see where the billiards come into the picture. So let's look at Lagrangian product. So Lagrangian product is I take two subsets of Rn and I take their product, just like for the just like it's written here. But it's Lagrangian because each factor is a Lagrangian submanifold. Okay, so I take the q coordinates in one and the p coordinates in the other. And then now, if we're trying to understand the symplectic topology of this, it will be useful, for example, to compute the minimum action or many other things, capacity-like things, to look at its boundary and at the characteristic foliation or the rate flow on the boundary. Okay, so the boundary of a product, I can think of the boundary of this product as the pre-image of 1, where by the function of the function h, where h is basically the maximum of the two norms, the norms defining the two convex sets. Okay, so the boundary at either the norm of k equals 1 or the norm of L equals 1. And then now I can look at what's the characteristic flow on this boundary. So let's do that. It's a very nice little exercise. So the characteristic flow, you can think of it as being generated by the Hamiltonian vector field. So the Hamiltonian vector field is just minus j times the gradient. And here it is, I computed it right here. So this new I is the normal, so it's a normal vector field to P, and then ddp, and then you have to multiply that by minus j. So let's see what happens when you flow using this vector field. And here, this picture that I'm going to draw is just a character. I mean, not a caricature, but like it's just an inspiration. Because of course you have these two different manifolds. So you have this corner. So you're either in k times the boundary of t, or you're in the boundary of k times t. But I think the picture will make sense. So let's suppose first that we are in the interior of k times the boundary of t. So then I'm going to follow this. And the other caveat is that this vector field is just continuous. It's discontinuous because the function is not smooth. But let's ignore that. Let's just follow this continuous vector field, this discontinuous vector field, and see what happens. Okay, so you start from a point in the middle of Q, in the interior of the disk of K, and on the boundary of T. And now we have to follow the normal vector field to P, and we have to make Q go in that direction, and then we leave the P constant. So this is what happens. I can't point because the laser is not strong enough, but I think you can see what's happening with my arrow. And then when you hit the boundary of both, then you're going through this corner. But there's a discontinuity. Now we're going to follow the other vector. So this is what happens. So now I'm going to look at the normal vector to minus Q, to Q, and I put the negative direction, and then I follow P in that. I make P go in that direction, and I leave Q constant. Okay. And then you go back into the original manifold, and then you follow again. You move Q in the direction of the normal to P, and you get this. And it's very easy to see that the blue angles are the same and the red angles are the same. So what that's saying is that these are actual billiard trajectories. So of course, my picture, it's pretty obvious because they're both disks in this picture. But this is true for other shapes. These will not be your usual billiards. These are called Minkowski billiards. So you see that the reflection in K is determined by the geometry of T. And the reflection in T is determined by the geometry of K. So these are basically two generalized billiard trajectories that are intertwined. In the case that you have two disks, there's going to be exactly two billiard trajectories. So you see that the rate flow on the boundary of a Lagrangian product is basically given by generalized billiards. Okay, so now I can kind of sketch the proof of that the Mahler conjecture is a consequence of Viterbo's conjecture. So it's actually very simple. There's just one calculation that they had to do. once you make this calculation, then the theorem follows. So the calculation is that the minimum action of the product of a convex symmetric set and its polar is always 4. And here it is. So if you take a symmetric set, you have to show this exists, of course. And computing that its action is always 4 is not that hard, because you have to compute, basically using the polar norm. But anyway, so this is the observation, and then you just plug it in, and then for the n over n factorial is exactly this minimum action over n factorial, and then the weak Viterbo conjecture will tell you that this quotient is bounded above by the volume of the symplectic manifold, and that's just the product of the volumes. So that's the Mahler conjecture. So, well, that's very nice. But what can we say about the equality case? So let's talk about that. So we can look at the product of the cube, the hypercube, and its polar. And it's not, we know that the hypercube should be a minimizer in Mahler's conjecture. So we can ask about whether the related domain, symplectic domain, what that has to do with Viterbo's conjecture. So it's not hard to see. You can do the calculation, see that this guy satisfies the equality of Viterbo's conjecture. And more generally, if K is a Hunter polytope, then it also does. Okay. And then the first theorem I want to mention to you is that I was able to prove with my collaborator Sepe that this product is symplectomorphic to a ball. This is kind of a sanity check, but it's highly non-trivial in a way. So basically we take the product of 2 polytopes, and I'm saying that's a symplectic ball. And a small detail here for the experts is that I don't go all the way to the boundary. So basically this is true for the interior. So the interior of this is symplectomorphic to the interior of the ball. It's not that crazy to believe in it, because if you look at this characteristic flow and the boundary of this product, this is going to be billiards, as I just explained to you, and this is Zoll. Like if you actually follow any billiard trajectory, you get back to the same point with the exactly same period. You have to play billiards in the hypercube with the geometry determined by the cross polytope. But if you're smart enough about how you do it, then you can figure this out. It still doesn't prove it's symplectomorphic to a ball, so we have to go deep into the interior to do that. But it's true. And then you can ask the same question about the Hunter polytope, not just the hypercube. Is it also symplectomorphic to a ball? And I claim that this conjecture is almost a theorem, but I don't want to claim that it's a theorem yet. So we're working on this, and I think we're nearly there, but it's a conjecture that it's, even for the Hunter polytopes, it still works. Okay, so this is what I kind of wanted to say about the Mahler conjecture, and now I want to kind of deep into similar issues for the Viterbo conjecture. Or issues about the Viterbo conjecture that are not necessarily related to Mahler. But before that, are there any questions or comments? Okay, so once you start playing with billiards, then you have fun, and then you can look at something else. So say that you take the product of a triangle and a hexagon. So it's actually not too hard, again, if you know how to play billiards like that, to prove that this Lagrangian product also satisfies the equality of Viterbo's conjecture. And now we're a little bit outside of the realm of the Mahler conjecture. And then you're like, okay, so is this still a ball? And the theorem that I'll show you in this slide is that it is a ball. And in fact, we can do something similar in all dimensions. So let me tell you what these polytopes are. So let's define these 2 polytopes, Sn and Rn. So these are, maybe it's not completely obvious that these are bounded polytopes, but they are. If you think about it just for a little bit, you figure out that Sn and Rn are polytopes. And actually Sn, it's not hard to see, it's a simplex. It's always a simplex. Rn is not a simplex, Rn is a more complicated polytope in general. But in dimension 2, S2 is the equilateral triangle, and R2 is the regular hexagon. Okay? So what we can prove is that the product of Sn and Rn is always symplectomorphic to a ball. You can prove that this product satisfies equality in Viterbo's conjecture. That's kind of a hard combinatorial thing, playing billiards in higher dimensions. I mean, Ostrover knows how to do that, and he checked. But our proof that of the symplectomorphism is independent, and it involves the total lattice, as I will explain in a little bit. So here's a picture of Sn and Rn when n equals 3. Okay, this polytope on the right is called the rhombic dodecahedron. Okay, so it's something that appears a lot. And one important comment about this, which will come up a little bit when you see the total lattice, is that this is related, if you know representation theorem, this is related to the root system AN. So the one, I mean, on the left, we have a simplex, and basically this is like the fundamental domain of the root lattice of AN. I mean, the fundamental domains, I think, are all simplices for every simple group. But I think the thing that's more interesting is that on the right, this rhombic dodecahedron, or the generalized rhombic dodecahedron, this Rn, is always what's called the Voronoi cell of the root lattice AN. Okay, this is just a comment for people who are inclined into representation theory. I won't really use it, but it's interesting to see how these polytopes come up in nature. Okay, any questions? So now let's talk about the total lattice, which is going to come up in this proof. The total lattice is actually a very famous Hamiltonian. I mean, I didn't really know it very well, but I know it's very important in the history of integrable systems. It's like the first interesting example of a nonlinear integrable system. So it's this Hamiltonian that I wrote up there. And the physical problem that it models is, think about a ring and n+1 particles traveling on the ring where they interact exponentially. So as they get closer, you have this potential that's getting bigger exponentially. So they will reflect. Okay, so this is the Hamiltonian system that H is describing. Okay, and one little comment before I continue is that it's not, maybe it's a little surprising that this comes up here, but it's not terribly surprising, because this exponential behavior, you can think of a limiting behavior where basically they don't interact at all until they actually crash. And when the two particles crash, they just reflect off of each other. So let me draw this picture. My hands, but suppose you have n+1 particles that are moving in some way, or you can think of a line, R mod Z or something. And then this system is, as they get closer, there's more and more potential energy. So they have this force going against. Or you can think of the limiting case, which is they don't have any force going against until they actually hit each other and they just reflect. And this system where they just reflect is actually equivalent to the billiard system in a simplex. That's actually a very simple change of coordinates. So in some way, this total lattice system is approximating billiards in a simplex, which is why you can think of one of the reasons why it comes up in this problem. Okay, so let's continue. So then Flashka had the idea of looking at this and changing coordinates in a kind of interesting way. This is not a diffeomorphism, but this will change coordinates and transform this Hamiltonian into something quadratic. And then we have the system here is the Hamiltonian system that we obtain. And a little caveat is that this transformation is not a diffeomorphism, and much less a symplectic. So basically, this system here you get by looking at the appropriate. You can look at the original system and push it forward by the coordinate change, or you can see how the Poisson structure in R2n changes. But anyway, if anybody is interested in knowing the details of this, I'm happy to explain later. Otherwise, I just sweep that under the rug. And then they realized, they realized in the 70s or late 60s, I think, that this system is equivalent to